Everybody, in this video we are going to look at manipulation of BGP inbound and outbound on a multi-homed site. So this is something that is seen quite often out in the real world. We've got an ISP up here, and then we've got a customer site down here, a large enterprise that is multi-homed to the ISP. So they've got two routers, and both those routers have got a connection back to the ISP. It doesn't necessarily have to be to the same router, but to the same ISP. I'm simulating that here with one router. So what we're going to look at doing is using some BGP attributes, namely the next hop self, the local preference, and the MED, or the multi-exit discriminator, also known as the metric within BGP, on how traffic flows out and how traffic flows in to the customer. So the network as it stands at the minute is just configured with the IP addresses. There's no routing protocols configured. That's what we're going to do firstly. So the AS in the ISP it's running BGP in AS 100, and we're going to have some eBGP relationships down here with the customer, and then within the customer site we're going to be running obviously eBGP with the ISP, but then we're going to be running ERGRP between these two routers to learn the internal prefixes within the organization. And then we've got a couple of PCs down here to test and to show traffic flows once we've configured all of the necessary steps. So if I move this across here, we'll start configuring. So on the ISP router, if we do a show IP interface brief, we can see we've got the two interfaces here that point down to the LUN1 and LUN2 routers, and then we've got a loopback here. So what we'll do is we will configure router BGP 100, BGP router ID, and then we'll do network of 80.1.100.1 with a mask, and then we'll do two neighbor commands. So 80.1.10.2 remote AS 65001, and then we'll do the same for 20.2. So we're advertising the loopback into BGP, and then we're setting up the neighbor relationships with LUN1 and LUN02. So if we come onto London 01, do a show IP interface brief, we've got the other end of the interface going up to the ISP. We've got one end of a backdoor link between London 1 and London 2, and then a loopback configured. So let's come into router BGP 65001. We'll set our BGP router ID to the loopback, and then we'll do two neighbor commands. We'll do one for the ISP router, so 80.1.10.1 remote AS 100, and then we'll do one for LUN2 because we're going to have an iBGP peering between the two London routers. So that will be 10.1.0.1 remote AS 65001, and we'll also configure for that one the update source as loopback 0, just because we're pairing on the loopbacks. That won't come up yet because we aren't running ERGRP, but what we'll do is here we've got the summary. So all of the IP space contained within this customer is using 10.1.0.0/16. So what we'll do is we'll advertise that to the ISP, say that was our IP block that we'd been given by them. Obviously that would be a public block in the real world, not an RFC 1918 block, but for this lab we shall use that. So we'll do an IP route to 10.1.0.0 with a /16 mask, and we'll send that to null 0. And also while we're here, we'll configure ERGRP, and we'll do 10.1.0.0 with a /16 wildcard. And then if we come back into BGP, so router BGP 65001, we can do network 10.1.0.0 with a mask of 255.255.255.0.0. So that's going to advertise this null route up to the ISP so that the ISP knows about us and our IP block. So that's all the configuration we need on there for now. If we come on to London 2 and do a show IP interface brief, we can see again we've got the other end of the transit network between us and the ISP. We've got the other end of the backdoor link, and then down here we've got two interfaces here configured as just internal networks to use these PCs for some verification of paths and to test some pings later on. And then we've also got a loopback. So if we first configure router EIGRP1 network 10.1.0.0 with a /16 wildcard, Mr. 25, and we see that comes up pretty much instantaneously. So we'll do the IP route for 10.1.0.0 with a /16 mask. Send that to null 0. And then we'll do the BGP configuration. So router BGP 65001, BGP router ID, and we'll also put the network in here first as well. So network 10.1.0.0 mask /16, and then we'll do two neighbor commands. So one for 80.1.20.1 remote AS 100, and the other one which is this iBGP pairing. So for that we'll do 10.1.0.2. The remote AS for that is 65001. Neighbor, not network. And then we'll also set the update source on that as well. So we'll wait for that to come up. There we go, the BGP relationship has come up. So what we've got now is we've got an EIGRP relationship between London 1 and London 2. We've got an iBGP relationship running between R3 and R2. And then we've got the eBGP relationships with the ISP, one for each of the London routers. So what we should see on both of the London routers, if we do show IP BGP, we're learning the 10.1.0.16 from the other London router through the iBGP pairing, and then we are also self-originating that. And then we're learning about the ISP's loopback from both London 1, from the ISP and through London 2, as we can see with this one here. So if we check that again on London 2, show IP BGP, we can again see that we're self-originating the 10.1.0.0/16. We're also getting it over the iBGP pairing, and then we've got two destinations for the loopback. The reason that this one hasn't been chosen here as the best, as you can see with the little greater than symbol here, is where we come into the first issue. The next hop for this is not reachable and is not in the routing table for London 2. If we do a show IP route, we do not see in here a route to get to 80.1.10 anywhere. So that's why this one has been chosen as best. What we can do to combat this and to allow this to be used as a backup route, because this would never, if this one failed, if this next hop failed, the loopback for the ISP would become unreachable, because this one will never be installed in the routing table because there isn't a route for this next hop. And the same thing is on here. So we see that this one has been chosen as the best because this IP address here, 80.1.20.1, which is this interface here, we don't have a route for it anywhere in the table. So 80.1.20.1 we don't have in the table. So what we need to do to combat that is, on both the London routers, we need to come into router BGP 65001, and then for the IBGP relationship, so from London 1's perspective, that is 10.1.0.1, we need to, on the neighbor command, set the next hop self attribute, and we need to do the same on London 2. So router BGP 65001, neighbor on this side is 10.1.0.2, and we'll do next hop self. So if we do a show IP BGP, that hasn't taken effect yet, so we'll do a clear IP BGP star soft. We'll do the same thing on London 1. What we should see if we do that now is that instead of before, where we had 10.1.10.1, well, sorry, 80.1.10.1 and 80.1.20.1, what London 1 has done is the route that it received from the ISP, when it has re-advertised that within BGP, or within IBGP, sorry, it has swapped the next hop to be itself, because before 80.1.10.1, from London 2's perspective, this IP address on this interface here was unreachable. It wasn't in its routing table, so if this had to fail over, it would not have a valid path to this loopback. So what adding next hop self has done, as it has allowed this second route to be put into the routing table if this one fails. So this one is best, as we can see by the little greater than sign. And because we've got a route and we can reach 10.1.0.2, because that's on a directly connected network, this in the BGP table is a valid route for if this one fails. So what we'll do is we'll verify that that's correct on London 1 as well. So show IP BGP. Yep. So we can see here that it's been swapped from, as the routes come in from the ISP to London 2, when London 2 has re-advertised it into IBGP, it has swapped out the next hop to be itself, hence next hop self. So what we can do to test this is, first of all, let's just check communication. So if we, from London 1's perspective, ping 80.1.100.1 from our loopback, we should see that works fine. And again from London 2, if we do the same thing, 80.1 100.1 sourced from our loopback, that's working fine. If we do a trace there, we should see that it's going straight up the interface here from London 2's perspective. If we just copy that command and put it on London 1, we see again it's going straight up the gig00 interface. So what we'll do is we'll come on to London 2 and we'll simulate a failure on this link going up to the ISP. A little quirk in GNS3, what I'll have to do is I'll have to shut it on both ends, otherwise the BGP session won't disappear for a lot longer than we would expect. So I'll shut it there, and then on the ISP side I'll shut it up here as well. So what we should see on London 1 is we see the BGP relationship go down. So if we do a show IP BGP now, this route now that we had before has been chosen as best because we have a valid route to the next hop. So we should still be able to ping the loopback on the ISP, and we can. And if we do a trace route, we can see that we can still get there, obviously because the ping succeeded, but we've got a 2-hop path now. So we're going from London 2, we're coming across to London 1, which is this address here, and then we're going up to the ISP, which is this interface address here. So if we just pull that interface back up, just to make sure that everything recovers. We should see that BGP relationship come up in a second. There we go. So if we do a show IP BGP now, and now we can see that this one has gone back to being the best because it's an eBGP relationship. So if we do a show IP route, we can see that our path has got an administrative distance of 20, whereas if we had this one, the administrative distance would have been 200 because it's iBGP. So the eBGP administrative distance wins, so that one gets installed in the routing table. So what we want to look at now is manipulating the inbound and outbound path that's taken for traffic leaving the customer and then traffic coming back into the customer. So on the ISP, if we do a show IP BGP, currently the traffic is coming in from the internet, quote unquote. The traffic will come down for the 10.1.0.0/16. It will come down this link here. So that isn't actually, if we do a clear IP BGP star, because that neighbor relationship on London 2 went up and down when we did the testing, it swapped these over. So yeah, that's what we wanted. We'll wait for the... So now it's been swapped to 20.2, which is this link here. So traffic coming into the customer's network from outside is coming down this link here. And the reason for that, if we do a show IP BGP and specify exactly that, what we can see is the reason that it's been picked as the best is because everything's the same up until the router ID. So the router ID on this router here is lower than it is on London 1. So the London 2 router ID is lower, so it's been picked as the best. So in a kind of real world scenario, let's say that this link was a metered connection, it was a slower connection, and we're paying quite a lot of money to put traffic up and receive traffic on that interface. So what we want to do is, by leveraging BGP, we want to push all traffic up this link here on London 1. Obviously this link we want to still use in the event of a failure, but all normal traffic should come up this interface, and it should also, when coming out from the internet to us, it should come down this interface. And obviously again, in the event of a failure on this link or a failure on London 1, the traffic wants to come down this link. So the way we're going to do that is, at the outbound traffic, we're going to use the BGP local preference, and for the inbound from the ISP to us, we're going to use the MED, or the multi-exit discriminator. So what we'll do is, if we do a show IP BGP, we can see that the local preference on these iBGP routes is 100, and the metric isn't set because it's not used by default. If we do a show IP BGP on here, again we can see the local preference is 100 on the iBGP routes. So in terms of local preference and metric, with local preference, the higher, the more preferred the route is, and with the metric, the lower the metric is, the more preferred that network or the next hop or the prefix is. So to achieve that, on London 1 we will configure a route map. So route map, we'll call it RM local pref and then what we want to do is we just want to set local preference to 120, which is higher than the default, so that means that this route is going to be preferred, or routes will be preferred. So we'll do that, and then what we need to do is we need to apply that within BGP. So the way local preference works is it will only take effect for the iBGP peering. It won't take effect for anything external over eBGP. It's hence the word local. It's local to the AS. So what we need to do is in router BGP 65001, we need to add this onto the neighbor command. So neighbor 80.1.10.1 with route map. We need to specify the route map name, and then what we'll do is we want to apply this to the routes coming in from the ISP. So we get the option for in or out, so we're going to choose in. So what we need to do now is do the same thing on London 1. So we do routes map. We'll copy the name from here, and what we'll do is we'll set local preference, and we'll set it on here to 110, and then come into router BGP 65001, and then neighbor 80.1.20.1 route-map. Put the name there, and then we'll choose in. So if we do a show IP BGP, it hasn't taken effect yet, so we'll do a clear IP BGP star soft. We'll do the same thing on London 1. So now if we do a show IP BGP, we can see that before, actually it's just above here, before the best route for the loopback was going to 80.1.20.1, which was coming straight up this eBGP link here. What we can see now, because we've set the local preference, we can see we've got the local preference here of 120. That's come from, so as this route has come down from the ISP to London 1, on ingress, London 1 has set the local preference to 120 with our route map. It's then advertised that into iBGP and sent an update across to London 2 with that local preference still intact. And then we have had our route come from the ISP for the loopback, and we've set the local preference to 110. And obviously with local preference, higher is better. So the 120 wins, which the next hop for that is 10.1.0.2. So that is the loopback here. So what we should see now, whereas before, if we were tracing to 80.1.100.1, sourcing from the loopback, it would have gone straight up this interface here. If we do that now, we should see that it goes to 10.1.20.1 first, which is London 1, and then it goes up to the ISP router. So what we're seeing here is the outbound traffic is now been manipulated to go across and up instead of directly up. So if this failed, so if something happened on London 1, or if something happened on this link here, this route would disappear from the BGP table and from the routing table, and this one would come back into effect, and the traffic would go straight back up this link. We can prove that by coming onto London 1 and going into interface gig 00 and shutting that interface down, and then the same on the ISP. If we go int, come into global configuration mode first, int G00, come into interface gigabit 00 and do a shutdown on there. So simulating some sort of an issue on this link here. If we come back onto London 2 and do a show IP BGP, we can see now that this has now disappeared, and the only route to the loopback is via the eBGP peering with the ISP. So we can still ping 80.1.100.1, sourcing from our loopback. So we've still got connectivity with the ISP and the broader internet, and if we do a trace route, we can see that the traffic is going straight up to the ISP. So if we allow this connection to come back, so we simulate the failure clearing and coming back online, wait for the BGP peering to come back up, there it goes, and then we'll give BGP a second to work out what's happened, and there we go, we've got the best route back as 10.1.0.2, which is the iBGP peering here. So we do a trace route again, and we can see that we're going back across the backdoor link and up to the ISP. So the issue we've got now is we've caused what's called asymmetric routing. So if we come up to the ISP, we do a show IP BGP again, our path to the customer prefixes is down the 10.1.20.2, or the next hop is 10.1.20.2, which is this interface here. So what's happening is if we're doing a ping from London 2, it's coming across, or if we're sending any kind of traffic, it's coming across to London 1, going up to the ISP, and then going wherever it needs to go, and then when it comes back into the ISP, the traffic is coming down this link. So that isn't ideal, because if the traffic is coming up here, we want it to be coming back down this way, and because we're wanting to utilize this link less because of whether it's cost, whether it's the bandwidth. There are valid use cases for asymmetric routing, but it's not best practice. So what we need to do now is use the MED, or the metric, to sway the ISP's judgment here and choose this as the preferred path down. And then obviously this path still wants to be in here, because if this link fails, like we just proved, we still want connectivity into the organization. So we're going to do this again with another route map on London 1 and London 2. So come out of here. So with route maps and the metrics for BGP, the lower metric the better. So what we'll do is on London 1 we will set the metric to 50, and then on London 2 we'll set it to 100, so that the ISP should prefer London 1 over London 2. So if we do a route dash map, and then we call it RM, and we call it BGP MED. Obviously you'd give it a better descriptive name in the real world, but for the lab it doesn't really matter, as long as we can tell what it means. So in here we'll do a set, and then we get lots of options in here, but we'll just do metric, And so on London 1 we're going to set it to 50, and then we need to come back into router BGP 65001, and again this is going to be applied for the neighbour for the eBGP peering, so 80.1.10.1 /map, and if we put the name in here, again we're asked in and out. We've already got a route map in, so we can't apply more than one in. So what we'll have to, well, we're doing this anyway, but we apply this out. So from London 1 we are sending the prefixes to the ISP, so they are going outbound, so we want to add the metric to the route outbound. So specify out, and then if we come on to London 2, go into global configuration mode, route-map, call it RM, what did I call it on London 1? BGP MED, BGP MED, and we'll set the metric. On London 2 we're making it worse than London 1, so we'll set it to 100. So then if we come into router BGP 65001, our neighbour is 80.1.20.1, specify route-map, and then we'll specify the name, and this is going to be outbound. So what we'll do is we'll do a clear IP BGP. Actually we'll do it on here first, just to stop the routes from flicking over. So clear IP BGP star, and then we'll do the same on here, just to make sure that everything comes back up properly and that the local preferences and the metric are being used. So on the ISP, if we do a show IP BGP, still doing some stuff, give it a second. So there we go, that's come back as we expect. So what we can see now is that we've got metrics here from the ISP's perspective. So the metric for the connection going down to London 1 is a metric of 50 as we set, and the route learned from London 2 has got a metric of 100. So from here, if we do a trace route to the loopback on London 2, so if we go 10.1.0.1 sourcing from our loopback, we should see that that is coming down this link here and it's coming across, so we're no longer using this link. So it's coming to 80.1.10.2, which is here, and then it's coming across to 10.1.20.2, which is here. And then we can verify again on London 2 that if we do a trace route out, so trace route 80.1.100.1 sourcing from our loopback, that is following the same route. So it's coming out of London 2 across to London 1 and then coming up to the ISP. So this interface here isn't being used. So what we'll do again is we will simulate a failure on this link. So if we come onto the ISP, go to global configuration and interface gigabit 00, if we shut that, and then on London 1 if we do the same thing, so that should pull that BGP peering down. What we see on the ISP side, show IP BGP, the 10.1.0.0/16 is still there, so we haven't lost communications to the customer, but the next hop is now 80.1.20.2, which is London 2. Likewise on London 2, if we do a show IP BGP, we haven't lost communications with the loopback, but instead of it going across to London 1, the next hop is now 80.1.20.1, and we can prove that in the routing table. We go BGP. We can see to get to 80.1.100.1, which is the loopback on the ISP, we're going via 80.1.20.1, which which is this interface here. So we should still have reachability. So ping 80.1.100.1 sourcing from our loopback. So we've got communication, and if we trace route to that, we can see that we're going straight there because obviously this link has failed. So to watch that recover, if we now shut these interfaces and wait for the BGP session to re-establish. Yeah, let's come back up. So again, we've gone back to having two paths to the 10.1.0.0/16, and the path down via London 1 is the best. We can prove that by looking in the routing table again for BGP, and we can see to get down to 10.1.0.0/16 we are going via London 1. And again on London 2, show IP BGP, we've got our two routes back going to the loopback on the ISP, and our favoured is going via London 1. So before it was going straight there because this link had failed. If we do the trace route again, we can see that it's going back across to London 1 and then across to the ISP. So if we come on to PC1 and PC2, so PC1 has got the IP address 10.1.90.2, which is here. The interface here is .1, which is configured as the gateway. And then PC2 has got the IP address 10.1.80.2, and its gateway is 80.1, which is this interface here. We have communication, or we should have communication with the loopback on the ISP, and we do. Verify that on PC2, 80.1.100.1. So we've got communication on both PCs. We verify the path. So if we trace to that, it's going up to its default gateway, it's going across to London 1 and then up to the ISP. So, and then again, if we do trace on here, so 80.1.100.1, we can see again it's following the same. It's coming up to its default gateway, it's going across to London 1, and it's going up to the ISP. So there may be a particular use case where you've got a specific prefix that you want to use this link. So in this example, we're going to choose this /24 here, this 10.1.90.0/24. We want anything on that subnet to, if it's coming down from the broader internet into the ISP, or from the ISP coming to us, we want it to use this link, and then traffic coming out of the enterprise network to the ISP wants to use this link. And again, we want this link to be utilized, or this path to be utilized in the event of a failure between ISP and London 2, so that this subnet doesn't get completely wiped off if this link or if something else fails here. So what we'll do is we need to manipulate that on London 2. So if we come onto here, what we need to do is we need to amend the route map that we used for the MED, and we also need to configure a prefix list. So what we'll do is we'll do an IP prefix list. We'll call it PL90net, and we will permit, and the network is 10.1.90.0.0/24. And then what we'll do is, if we do a do show prefix list, we want to look at the route maps. So we've got the route map BGP MED here. The first sequence is 10. So what we set on London 1 for the metric was 50. So what we'll do here is we'll do route-map, and what we'll do is we'll specify the sequence number of 5. So that's going to come before this sequence, which sets everything to 100 on the metric. And then what we'll do is we will match IP address prefix list, and then we'll specify our prefix list. And then we can either leave the metric to default, or what we'll do is we'll set it to 50, just so we can check that it's definitely working when we go onto the ISP router. So we set the metric as 50. So what we'll have to do is do a clear IP BGP. In fact, what we actually need to do as well is we need to advertise a specific prefix up to the ISP. So at the minute the ISP knows about the broader 10.1.0.0/16, but it doesn't know, and we need to advertise it a specific route for this 10.1.90.0. So what we'll do is we'll come into already in configuration mode. We'll come into router BGP 65001, and we'll just do network 10.1.90.0 with a /24 mask, and then we'll do the same on London 1. Router BGP 65001 network 10.1.90.0. Specify the mask. So if we come on to the ISP, do a show IP BGP, we can now see that we are receiving 10.1.90.0, and actually we need to set the metric. What's happened here is we're setting the metric on London 1 to 50, and we've also just set the metric on London 2 as 50 as well, although at the minute it is preferring, and it's saying that the path down to London 2 is the best. We want to make this metric a little bit smaller to make sure that it definitely wins every single time. So what we'll do is we'll come back into here, and we will do show route-map. What did we call it? BGP MED. So if we do route-map BGP MED 5, we will match IP address prefix list PL90net, and we will set the metric, and we'll do 25. Oops, space there, 25. So let's see if that's taken effect. We'll do a clear IP BGP starsoft. So here we go. The metric has now changed to 25. So what we should see is if we trace route still go into 10.1.0.1, so if we trace route from the ISP to the loopback on London 2, as we would expect, if we source this from our loopback, this should go down to London 1 and across to London 2, and it does. But now if we trace route to 10.1.90.2, which is the PC here, we see that although the PC, there we go, something happened there with the PC, obviously didn't respond in time, but the path now is coming straight down here and straight down to this PC. So for this specific /24, we're coming down the route to London 2 and then coming down here. The issue we have now is back on PC 1. Obviously we can still communicate with the loopback, but if we still do a trace route, we're seeing that we are going across to London 1 again. So we've got 3 hops in here. So we're coming up, we're coming across to London 1, and we're coming up to the ISP router. So again, we've created a scenario with asymmetric routing. So if we're sending out traffic, it's coming across this way, and traffic coming back to us is coming down this way. So what we need to do is we need to set up some policy-based routing on London 2 to make sure that any traffic from 10.1.90.0/24 is going up this interface here. So if we come on to London 2, what we'll have to do first is specify a access list to catch the source traffic. So we'll do an IP access list extended 101. We'll permit IP, and then the source is 10.1.90.0 with a /24 wildcard, and we're going to any destination. So then what we need to do is we need to specify a route map. So route map, call it RM 90 net. We'll call it PBR for policy-based routing. And then what we'll do is we'll match IP address 101. So that's matching the IP address or the source network in the access list 101. And then what we'll do is we'll set IP next hop, and we'll set that to 80.1.20.1. So what that's going to do is that's going to override the routing table, and if traffic comes in on whatever interface we apply this to, if it comes in from this source network, it's going to override whatever the routing table says and send it to 80.1.20.1, which will send it up this interface here. So what we need to do is we need to apply this on an interface. So we'll apply it on gig 6/0, which is the interface here. So we'll apply that by doing IP policy route-map, and then we'll specify the name, which is here. So that's applied, and that will apply on ingress to this this interface. So the traffic coming in and going out will basically get caught by this route map. What we'll do is we'll put some debugging on. So we'll do debug IP policy, and this has turned up policy routing debugging on. So what we should see now is if we come onto PC1 and we do some pings, we've still got communication. So we haven't lost communication. And what we can see is on London 1. So we can see that here we've got policy routed. So what this has done is it's used our policy-based routing route map, and it's sending the traffic up to the ISP on gig 00. We can prove that by doing a trace route. So before we were coming up to the default gateway, we were coming across to London 1, and we were going up to the ISP. So if we do this now, we'll see that we're hitting the default gateway, and then we're going straight up to the ISP. We're no longer going across to London 1. So we can verify that again by doing a trace route on here, and again we're still following this route down here. So we've now eradicated the asymmetric routing problem. So traffic coming from the 10.1.90.0/24 network is coming up to London 2 and going straight up to the ISP, and then traffic coming back down, destined for the network, is coming straight back down to London 2 and back down to whatever PC or device it was meant for. One thing to verify is that if this link here fails, obviously we've got policy-based routing telling the router to override the routing table and send traffic up here. So we need to make sure that the traffic is still going to flow across this way and still flow down this way to get to the 10.1.90.0/24 network if something happens with this interface and this BGP pairing between the ISP and London 2. So what we'll do is we'll come on to London 2 and we will simulate a failure. So we'll come into gig 00 and we'll shut the interface down, and we'll do the same on the ISP just to make the BGP session disappear faster. So in G01/0 and we'll shut that down. So if we come on back onto PC1, we've still got communication with the loopback, and if we look at the debug output, so the policy has been rejected because the address is no longer attached. So the next hop has been rejected. So you can see here next hop rejected, and then it says normal forwarding. So what that's done is policy-based routing has got a fallback where it will check the next hop you've set, and if the next hop isn't reachable, then it will do what it says here. It will do normal forwarding. So we haven't lost communication with the ISP, and again if we do a trace route, we should see that it's following the route going across from London 2 to London 1 and then back up to the ISP. So that concludes this video. What we've managed to do is manipulate the inbound and the outbound traffic flows for a multi-homed site using BGP, and we've also thrown a bit of policy-based routing into there. I hope this video has been helpful.